Hey, everybody, and welcome to 6-2 Real Applications of Normal Distributions. This section presents methods for working with normal distributions that are not standard. Standard, remember, was the mean is 0. Here, the mean is not 0. And it could be the standard deviation is not 1, or both of those could be true. The key is that we use a simple conversion that allows us to standardize any normal distribution so that the same methods of the previous section can be used. There's our formula. Z equals X. X is the value that you're using to find the probabilities. This formula allows us to standardize any normal distribution so that the X values can be transformed to Z scores. Let's say you start off with a normal curve and our mean is 100, mu equals 100, and our standard deviation is equal to 5. Our Z number is equal to some X minus 100 divided by 5. Let's make X equal 110. And the problem will state what X is. We would have Z equals 110 minus 100 divided by 5, which is 10 over 5, which is 2. Our Z number is 2, which means we're 2 standard deviations away from the mean. This would be 2 standard deviations, which is true because my standard deviation is 5, and I picked 110 for X. 1 standard deviation would make it 105. 2 standard deviations would make it 110. We normalized it. What proportion of men are taller than the 72-inch height requirements for shower heads? Stat, calculators, normal. And in here, it just comes up with mean is 0 and standard deviation is 1. I could change it into a Z-score, but I don't need to because I can just change this to the mean is 68.6. The standard deviation is 2.8. And I'm looking to find the percentage of men who are taller than the shower head, and the shower head is 72 inches. And now this is the probability that men are greater than 72 inches tall. 0.1123. We could also convert 72 inches to the Z-score by using Z equals X. X is 72 minus mu, which is 68.6, divided by 2.8. That would give me a Z-score of 1.21. Now, if I use our regular calculator with the mean equals 0, standard deviation of 1, we converted the Z-score to 1.21, and we hit compute. That's a little bit off from what we had before, which is 0.1123 or 11.23%. But it's because we rounded to 2 decimal places. If I use the number that I get and don't round it to 2 decimal places, we get 0.1123, which is 11.23%. The interpretation: the proportion of men taller than 72 inches is 0.1123. Multiply that by 100 and you get 11.23%, which means that about 11% of men may find the design to be unsuitable. Finding values from known areas. Here are some helpful hints for those cases in which the area or probability or percentage is known and you must find the relevant value that goes with it. Graphs are extremely helpful in visualizing, understanding, and successfully working with normal probability distributions. They should always be used. Don't use Z-scores and area. For example, I have a normal curve, And these numbers on the horizontal axis are my z-scores. This is 1, 2, -1, -2. This is also mu, and this is where z equals 0. Z equals mu equals 0. And then sigma is equal to 1. We've made it so that our mean is 0 and our standard deviation is 1 by converting to a z-score. Z-scores are distances along the horizontal scale. But if I wanted to know the probability that my value is less than or equal to 1, this is my area from the left to the value that I picked for my z-score. Here I picked 1. X is less than or equal to 1, I would get the area, which is the same as the probability. But is not the same as the z-score. We could even find out what it is. Let's pull up our StatCrunch. And now we've normalized it. So we made mean is 0, standard deviation is 1. I want to find x is less than or equal to 1. I hit compute and I get my answer, which is 0.8413 or 84.13%. This is the probability, the area under the curve on StatCrunch. This is the probability. This is my z-score. If I wanted to know the probability that it's greater than 1, now it's highlighting the other side, and this would be 1 minus 0.8413. The area in red is the probability, and the z-score is at the bottom. We have to choose the correct left or right side of the graph. If it says a graph separating the top 10% from the others will be located on the right side. If I bring back my StatCrunch, choose the correct side, right, left side of the graph. A value separating the top 10% from the others. I don't know the z, but I know the probability is 10%, which would go in here. That's my z-score that separates the top 10% from the others. Will be located on the right side of the graph. But a value separating the bottom 10%, I hit less than, and here's the bottom 10%. This is going to be the same number, except it's negative. But negative 1.28, positive 1.28. They're the same z-score, one's positive and one's negative. A z-score must be negative whenever it is located in the left half of the normal distribution, because remember, our normal distribution looks like this. Here's the mean. This way are negative z-scores, and from here this way are positive z-scores. Areas or probabilities are always between 0 and 1, and they are never negative. This is less than or equal to some number. This is greater than or equal to some number. Procedure for finding values from known areas or probabilities. We would sketch a normal distribution curve, enter the given probability or percentage into the appropriate region of the graph, and identify the x value being sought. And if you know the z number, we must convert it. We have to know the z number, we have to know the standard deviation, and we have to know the mean. And remember, our formula was z equals x minus mu over sigma. I'm going to multiply both sides by sigma. This sigma would cancel with this sigma. My next line would be sigma times z is equal to x minus mu. And if I want to solve for x, I just add mu to both sides. That would give me mu plus z times sigma equals x. Same formula. We have different information, so we're using it a different way. Refer to the sketch of the curve to verify the solution makes sense in the context of the graph and in the context of the problem. For example, if you got probability that was greater than 1 or less than 0, that's wrong. Think about your answers and does it seem logical? Example, with the shower, proportion of men that are taller than 72 inches, that's 6 feet tall. 11.23%, that makes sense. There's people that are shorter than 6 foot tall. There's people that are taller than 6 foot tall. But given all the information that we have, 11.23% of men are taller than 72 inches. When designing equipment, one common criteria is to use a design that accommodates 95% of the population. We have seen that only 46% of women satisfy the height requirements for U.S. Air Force pilots. What would be the maximum acceptable height of a woman if the requirements were changed to allow the shortest 95% of women to be pilots? That is, find the 95th percentile of heights of women. To my normal calculator, our mean is 63.7. Our standard deviation is 2.9. We want to know the value where the probability is less than 0.95. I hit compute and I get 68.47. That the Air Force can set the maximum height of a woman to 68.47, and that would allow them to accept 95% of women. The area of 0.95, that's what I put over here on the right side, corresponds to a z-score of 1.645. That's if I leave the mean to be 0 and the standard deviation to be 1. Then I could use my formula, put in all the values, and I would end up with x equals this value, which equals 68.4705, which is pretty close. This is a little different than the value that we got here, but close enough. We found x using StatCrunch, or we can find x using that formula.